Okay, so in our first example, we're going to produce some examples of harmonic functions using the fact that we know certain functions are analytic. And so the function we're going to start with here is z squared. Z squared is entire. That is, it is analytic on all of the complex numbers. So it's an entire function. And so, by what we said in the previous video, the real and imaginary parts are harmonic. So we're going to go and we're going to check that um, with this very particular example. So we've actually already worked out the real and imaginary parts of this function a couple of times. The real part is x squared minus y squared, and the imaginary part is 2xy. So here, let's use maybe a lighter blue. Here our u is x squared minus y squared, and our v is 2xy. Uh, okay, so the claim is that, well, we've already proven the claim, but u and v are harmonic, just to use the uh, language we're introducing. So this means that nabla squared u is 0 and nabla squared v is 0. All right, so how do we show this? So let's check nabla squared u is 0. So nabla squared u is partial squared u partial x squared, and the second derivative of u with respect to y squared. All right, so let's differentiate our u, which is x squared minus y squared, twice with respect to x. You're going to find that it's 2. And then we're going to differentiate u with respect to y twice. You're going to find, well, there's a negative sign, so it's going to be negative 2. 2 minus 2 is 0. Great. It is harmonic. Now let's check nabla squared v is 0. So again, nabla squared v, or the Laplacian of v, is partial squared v partial x squared plus partial squared v partial y squared. Partial squared v partial x squared, what's v? V is 2xy. If we differentiate v once with respect to x, we get 2y, and again with respect to x, we get 0. So both of these are 0. So is it harmonic? Yeah, we get 0. Awesome. Cool. So here's our first example of explicitly checking the real and imaginary parts solve Laplace's equation.